Dear students, today I am giving the 7th video on topology. It is the continuation of the last class. Let's see, we'll discuss first theorem. Let E alpha to alpha in index set be a collection of connected subspaces of a topological space X2, and let A equal to union A alpha, and the following are true. Part A, if intersection A alpha not equal to phi, then A tau A is connected. Part B, if for each A, B elements of capital A, there is a connected subspace capital B of A, capital A, such that A and B elements of B, capital B, then A tau A, the space A tau A is connected. Part C, if the index set is taken as En and An intersection En plus 1 not equal to phi for each n element of capital N, then the space A tau A is connected. There is 3 parts are there for the theorem A, B, C. We will discuss the proof of the same. First we discuss part A, proof of part A. What is given? Suppose that intersection E alpha not equal to phi. We have to prove that A tau A is connected. If possible, A tau A is not connected. That is the argument, negation argument. Then what about that a separation can be taken. Let A equal to C union D be a separation of A. That is C and D form a separation of A. Let beta element of the index set. Then A beta is subset or equal to A. What is A? A is C union D. Since A beta is connected by the previous theorem we discussed in last video, we have A beta is subset or equal to C or A beta subset or equal to D. Take the first case, assume that A beta subset or equal to C. To each alpha in the index set, we have A alpha intersection A beta not equal to phi. Otherwise what will happen? Otherwise intersection A alpha must be equal to phi. So A alpha intersection A beta not equal to phi. Then A alpha is subset or equal to C for all alpha, because A beta is already subset or equal to C. So this implies that is A alpha subset or equal to C for all alpha. This implies union A alpha that is subset or equal to C. But a union A alpha that is A subset or equal to C, a contradiction. Because in that case what you will get? Actually what is A? A equal to C union D. A is subset or equal to C. Then automatically D equal to phi. And that is not true. That you cannot take. That's why A subset or equal to C is a contradiction. Hence our assumption is wrong. That means A to A is connected. Now taking part B, proof for part B. Suppose for each AB elements of A, there is a connected subset capital B of A such that both AB are elements of B. So fix X in A. Then for each Y in A, there exists a connected subset AXY, A suffix XY of capital A such that X and Y are elements of AXY. Then what is A? A is union of such AXYs, where Y is element of A. Clearly, X is an element of intersection AXY, because X is an element of AXY for all Y in A. Thus we get intersection AXY that is not equal to phi, or union of AXY is connected. That follows from part A, or A to A is connected. That's all about the proof for part B. Now discussing part C. Suppose that An intersection An plus 1 not equal to phi for all n in N. You take a Bn equal to A1 union, A2 union, etc. union An. Now we show that Bn is connected. We are proving it by using the induction method. So we take B1 equal to A1 which is connected. Assume that Bn is connected. To prove that Bn plus 1 is connected, so consider Bn plus 1. What is Bn plus 1? A1 union, A2 union, etc. union An plus 1. It's equal to Bn union An plus 1. We have An intersection An plus 1 is subset or equal to Bn intersection An plus 1. So, but we know An intersection An plus 1 is not equal to 5. Therefore, what do you get? Bn intersection An plus 1 is not equal to 5. Now Bn union An plus 1 is connected because Bn and An plus 1 are connected. This implies Bn plus 1 is connected. Thus Bn is connected for all n in n. Follows from induction. Now intersection Bn, that is B1 intersection, B2 intersection, B3 intersection, etc. that is equal to A1 intersection B2. What is B2? A1 union A2. Then B3 A1 union A2 union A3. In that we are writing A1 intersection, A1 union A2 intersection, A1 union A2 union A3 intersection, etc. That means A1, this is what A1 only are getting, and A1 is not equal to 5. Or union Bn is connected. That shows that the union An is connected. That's how the proof of the theorem. All the three parts are proved. Next definition we are taking, that X2 be a topological space and define an equivalence relation tilde on X as below. X tilde Y if there exists a connected subset A of capital X such that X and Y, small x and Y elements of A. That's what X tilde Y. X tilde Y if there exists a connected subset A of X such that both X and Y are elements of A. The equivalence classes of X with respect to the equivalence relation tilde are called the components of X. They are called the components of X. Verification, X tilde X, because set X is a connected subset of X. If X tilde Y, then clearly Y tilde X. So reflexive, symmetry also true. Next, to prove the transitivity, suppose X tilde Y, Y tilde Z, then there exists connected sets A and B such that X, Y elements of A and Y, Z elements of B. Then Y is an element of A intersection B. That shows that A intersection B not equal to 5. Or A union B is connected and both X and Z elements of A union B. That shows X tilde Z. Hence Z is or transitivity is true and X tilde is an equivalence relation. Now we can discuss the remarks. Remark 1. If C is a component containing X, then C is a maximal connected subset of X containing X. So components are the maximally connected subsets. That way we are arriving at the argument. And second remark is, if X itself is a connected set, then there exists only one component of X, namely capital X. The space X itself is connected, and there exists only one component of small x, that is namely capital X itself. Theorem: every component of a topological space X2 is a closed subset of X. Every component of a topological space X2 is a closed subset of X. We'll prove it. Let A be a component of X. Let prove that A is closed. Let small x element of A. Then A is a maximal connected set containing X. That's the remark. But if A is connected, then A closure is connected. And that A closure is a subset or equal to A. Because A is the maximal connected set. You can call it as 1. But we know that A is always subset or equal to A bar. That is result 2. From 1 and 2 we get to A equal to A bar, or A is closed. Next definition. A topological space X2 has the fixed point property if for each continuous function f from x to x, there exists small x in x such that f of x is x itself. Image of small x under f is the same small x. That is what we called the fixed point property. Theorem: the closed unit interval I, what is I? Closed interval 0, 1, has the fixed point property. Proof: let f from I to I be continuous if f of 0, that is what is I? I is closed interval 0, 1. So f of 0 equal to 0 or f of 1 equal to 1, then there is nothing to prove. So let f of 0 not equal to 0 and f of 1 not equal to 1. F of 0 not equal to 0, this implies f of 0 must be greater than 0. F of 1 not equal to 1, that must imply f of 1 less than 1. You are defining a new function g from I to I by g of x equal to x minus f of x. Then what will be g of 0? 0 minus f of 0, that is less than 0 because f0 is greater than 0. G of 1 is 1 minus f of 1, that is greater than 0 because f of 1 is less than 1. Clearly, g is a continuous function and g of 0 is less than 0, which is less than g of 1. Then by the intermediate value theorem, last class we have studied, last video it is there. Then by the intermediate value theorem, there exists some x in I such that g of x equal to 0. What is g of x? That is x minus f of x equal to 0 or f of x equal to x, or x is a fixed point. Hence, the interval I has, interval I equal to 0, 1, closed interval 0, 1 has the fixed point property. One more theorem we can discuss there. Theorem: the fixed point property is topologically invariant. The fixed point property is topologically invariant, means it is a topological property. Proof: suppose capital X has the fixed point property. Topological property in the sense we have already studied topological property. We have to discuss under a homeomorphism. So let h from x to y be a homeomorphism to prove that y has the fixed point property. X has the fixed point property means y should have the fixed point property under the homeomorphism. That is what the argument. So that is what we have to prove. Let f from x to y be a continuous function, and that is marked here. H is from x to y, f is from y to y, so that f composite h is from x to y. F composite h from x to y is continuous because composition of two continuous functions once again continuous. So whatever the map h inverse of f composite h, that is clearly from x to x. H inverse of f composite h. H inverse is from y to x. F composite h is from x to y. So that h inverse composite f composite h is from x to x, which is continuous. Since x has the fixed point property, there exists a small element, that is there exists an element a in x such that h inverse of f composite h of a equal to a. This implies h composite, h inverse composite f composite h of a is what? H of a, or f composite h of a, that is what? H of a, or f of h of a, that is what? H of a. That shows that f has the fixed point property and the fixed point is h of a. That is, f of h of a is h of a, or h of a is the fixed point. That shows that capital Y has the fixed point property. That's all about the video, and you discuss the notes properly and discuss it, read it properly, discuss the nodes, and any doubts means mark it out.